Hi, in this video I am going to explain about metal carbonyls. What are metal carbonyls? Metal carbonyls are organometallic compounds. What are organometallic compounds? Organometallic compounds are those compounds in which there is a metal carbon bond present. Example, Grignard reagent. Grignard reagent has a general formula RMGX, where R is a hydrocarbon part. It can be alkyl group or aryl group. Mg is a group 2A metal. X stands for halogen. Here X can be chlorine, bromine, iodine, but not fluorine. Now, if I take a specific example, CH3MgCl, methyl magnesium chloride. Now, here this carbon of the methyl group is bonded to magnesium. It is attached to magnesium. So, this can also be written like this: CH3. Because carbon is more electronegative than magnesium on Pauling scale, carbon will get a partial negative charge, magnesium will get a partial positive charge. Now here carbon is bonded to magnesium. So it's an example for organometallic compound. Another example is metal carbonyls. Metal carbonyls like NiCO taken 4 times, nickel tetracarbonyl. Here carbon is covalently, actually coordinate covalent bond is present between nickel and CO. So carbon is covalently rather bonded to nickel atom. Now if we take a specific case of this example of metal carbonyl, NiCO taken 4 times, how and why the formation of NiCO4 takes place, we will discuss here. Now NiCO4, now what is the key points present in this complex? This is a complex coordination compound. Nickel is a central metal atom. CO is a ligand. It's a strong field ligand. Now what do you mean by a ligand? Ligand is any species which can donate the electron pair. An electron pair donor is called as a ligand. And in ligands, CO is one of the strongest field ligand. Now nickel is surrounded by 4 ligand molecules. CO is a neutral molecule. Now this 4 represents a coordination number. What do you mean by a coordination number? Number of surrounding atoms around central metal atom is called as coordination number. So nickel has a coordination number of 4. So if you look at the structure of nickel tetracarbonyl, nickel is surrounded by 4 CO molecules. Like this. Now if you look at the arrangement of this molecule, it is tetrahedral. So what is the geometry of nickel tetracarbonyl? If the coordination number of any complex is 4, there are 2 possibilities. One is that the complex can be square planar complex or tetrahedral complex. Now in this case, coordination number of nickel is 4 and the geometry is tetrahedral. It's a tetrahedral complex. It's a tetrahedral complex. Now, why nickel? Now the question comes, why nickel is surrounded by only 4 CO groups? Why not 5? Why not 6? Why not 3? The answer comes from EAN rule, Sedgwick's effective atomic number rule. What it says? It says that if any complex is having nearest noble gas configuration towards the central metal atom, then that complex will be stable. It means if अगर आप कोई कोऑर्डिनेशन कंपाउंड लेते हैं तो उसके अंदर जो सेंट्रल मेटल एटम होता है वो अगर लाइगैंड के साथ कोऑर्डिनेट कोवलेंट बनाने के बाद अगर नियरेस्ट नोबल गैस कॉन्फ़िगरेशन अटेन कर लेता है तो वो कॉम्प्लेक्स स्टेबल होता है. सो इफ यू टेक निकल in the nickel tetracarbonyl complex, nickel atomic number is 28 and its outer electronic configuration is 3d8 4s2 4p0. Now you know that the fourth shell is the valence shell, last shell. Third shell is the last but one shell. Now, if you take CO, as I said earlier, that CO is a strong field ligand. According to valence bond theory, a strong field ligand can cause force pairing of electrons in the central metal atom. So, this COs, when they come close to the nickel, the s electrons that are present in the last shell, that will get force paired up. They enter into the 3d orbital and pairing will take place. If you take 3d has 8 electrons. These are the 5d orbitals of 3d and each contain 1 electron each. Then here pairing is done. This is 3d8 configuration. 4s, if you take, there are 2 electrons. So now when CO comes close to this nickel atom, these electrons from S, they get migrate to 3d, thereby causing the pairing of these two unpaired electrons. These get paired up. So when they get paired up, now the configuration will change for the nickel. Now the NiCO4, when 4 COs come close to nickel, now nickel has the configuration 3d10 and this is 4s0 and this is 4p0. Now one s orbital and 3 p orbitals are empty. Right. Now we talked about two things. One is hybridization, one is the geometry of the NiCO taken 4 times. It is tetrahedral. Tetrahedral means hybridization will be sp3. So you can see very clearly here, one s orbital and 3 p orbitals are available for bond formation. So one s orbital and 3 p orbitals are available for bond formation. This is 4s and this is 4p. So each CO will donate one electron pair. Each CO will donate one electron pair to the empty orbitals of nickel. So like this, sp3 hybridization takes place and nickel tetracarbonyl has tetrahedral geometry. Now the question arises, why only 4 COs are participating in bonding? Why not more than that or less than that? The answer comes from EAN rule. What is EAN rule? Effective atomic number rule. EAN rule EAN value can be calculated as Z minus oxidation number plus 2 into coordination number. Z stands for atomic number, right? So now if you take nickel tetracarbonyl, the atomic number of nickel is 28 minus, what is the oxidation state of nickel? See, if you take the metal carbonyls, remember central metal atom will have 0 oxidation state because CO is a neutral molecule. How many neutral molecules are there? 4 in number. So what is the total charge for 4 COs? It is 0. Now what is the charge on the complex? It is 0. If nothing is written on the square bracket, it means that it is having 0 charge, total charge, right? So when you are going to get the total charge 0 here, when you sum the oxidation numbers or charges on nickel and 4 COs, if you sum this, you should get 0. So if I assume that the oxidation state of nickel is X, I don't know what it will be. And I know already CO is a neutral molecule, so it do not carry any charge. Like that there are 4 COs, so total charge will be 0 here. So if I sum one nickel atom into its oxidation state, that is charge, plus 4 into its charge of each CO molecule, it should become how much? It should be equal to 0. So X plus 0 is equal to 0. So X is equal to 0. So from this, what I got is nickel oxidation number is 0. Charge on nickel is 0. So now oxidation number is 0 plus 2 into, what is meant by coordination number? Coordination number is nothing but number of surrounding atoms around central metal atom. As you have seen already in the diagram, nickel is surrounded by CO. So what is the surrounding atom around nickel? Carbon. It is not oxygen. Who is bonded to nickel? Carbon. So directly linked atoms, how many they are around the central metal atom? That you have to count. That count is nothing but coordination number. So from each CO, one carbon is directly linked to nickel. So like that 4 COs, 4 carbons are directly linked to nickel. So coordination number is 4. So now 2 into 4. This is 28 plus 4 2s are 8. This comes to 36. Now 36 is the configuration of what? Krypton. Because nickel atomic number is 28, nickel atom is close to which noble gas atom? Krypton. Not helium or neon or xenon or radon. So according to Sidgwick's concept, if any central metal atom of the complex attains nearest noble gas configuration after forming a coordinate covalent bond with the ligands, then it will be stable. So now by bonding with 4 COs only, the nickel atom is attaining 36 atomic number, that is krypton configuration. So it is stable. That's why nickel bond with only 4 COs, not more than 4 CO or less than 4 CO. Now let us go into the details of the bonding. So generally, if you take a metal and CO, this is the Lewis structure of CO. Now central metal atom is what? Nickel. Now the question arises, why carbon only bond with nickel? Why not oxygen? As I said earlier, ligand is the electron pair donor. So ligand can form a coordinate covalent bond with the central metal atom. You know, nickel has the empty d orbitals. So let us say this is one d orbital. Generally, d orbitals will have double shape, with exception of course. So now this is the 4 lobes of d orbitals I am showing, which is empty. Now why carbon only donate the electron pair? Why not oxygen? Both are having the lone pairs. The answer is, if we calculate the formal charge on carbon, it is -1. If we calculate the formal charge on oxygen, it is +1. So which is having more negative charge? Carbon, not the oxygen. Because carbon is electron rich, it has more ability to donate the electron to the central metal atom in preference to oxygen. So it is carbon which donate the electron pair, which give the electron pair to nickel, not the oxygen. So thereby what happens? Between nickel and CO, a coordinate covalent bond is formed. So like this, 4 CO groups will form a coordinate covalent bond with nickel, thereby forming NiCO taken 4 times. So now, because according to valence bond theory, between 2 atoms, if only one bond is formed, that bond is always a sigma bond. So which bond this is? This is a sigma bond. So first, a sigma bond is formed between a metal and carbon. Now, because carbon is pushing its electron density towards nickel, the electron cloud is flowing towards nickel. Nickel is a metal. Metal has ability to lose the electron, not ability to gain the electron. So due to surplus or excess negative charge on nickel due to this donation will make nickel unstable. निकिल जब CO से इलेक्ट्रॉन्स लेता है तो वो अनस्टेबल हो जाता है, क्योंकि उसके पास इलेक्ट्रॉन की डेंसिटी बढ़ जाती है, क्योंकि वो मेटल है. मेटल तो इलेक्ट्रॉन गेन नहीं करना चाहता, तो उसके पास इलेक्ट्रॉन डेंसिटी बढ़ जाती है. सो दैट्स व्हाई इन ऑर्डर टू stabilize it, nickel, what it will do is, after making a sigma bond, it take the help of its filled d orbitals. These are the filled d orbitals of nickel. Filled d orbitals of nickel, and you have empty pi star orbitals. Empty pi star orbitals of CO. CO is a molecule. According to molecular orbital theory, in CO there is an empty pi star orbital present. So now nickel will push back donate the electrons to CO, because उसके सर पे जो चार्ज होता है वो बढ़ गया है, नेगेटिव चार्ज, and it does not want it. So in order to stabilize itself, it will push the electron density towards the CO molecule, and that electrons are entering into the anti-bonding molecular orbital. So according to molecular orbital theory, if the electrons enters into the anti-bonding molecular orbital, it become unstable, right? So CO is becoming unstable. Nickel, by pushing the electrons towards CO, it is becoming stable, right? So now already there is one sigma bond formation. Now due to this back donation tendency, which we also called as synergistic effect. Synergistic effect means what? Mutual stabilization. Mutual stabilization means first nickel is stabilized due to formation of CO, sigma bond formation. Then by back donation, another bond is formed, that is a pi bond. This is a pi bond, half pi bond above, half pi bond below. So sigma bond is stabilized by pi bond is stabilized by sigma bond. Like that, mutual stabilization is taking place. Now, because nickel has pushed the electrons into the empty pi orbitals, anti-bonding molecular orbitals of CO, now this CO is becoming unstable. Actually, CO molecule, if you take free CO molecule, it is stable. When it is not bonded to any central metal atom, it is stable, because its bond order will be 3.0. Its bond order is 3.0, right? So now after the back donation, the bond order of CO, it will be less than 3.0. Less than 3.0. Now why the bond order is decreasing? Because the stability of CO molecule is decreasing due to this back donation, due to this synergistic effect. So now what is the bond present between the central metal atom and CO? Between central metal atom and CO, it is neither a sigma bond, neither a single bond nor a double bond. What is the bond order here? Bond order, you should not say 2, because here this push is not complete. There is a flow of electrons taking place. You can say here a partial double bond character is generating between nickel and CO. Now what about the bond between carbon and oxygen? It is neither a double bond nor a triple bond. So this bond, it will be between 1 and 2, and this bond order, it will be between 2 and 3. So due to this back bonding or synergistic effect, the bond orders will change. So when pi bond is not formed, when there is no synergistic effect, bond order is 1. One sigma bond is formed between nickel and CO. So bond order is 1. Now due to back donation, the bond order is neither 1 nor 2. It is between 1 and 2. Earlier, when CO is alone, bond order is 3. But now due to back donation, it is less than 3. That is between 2 and 3. So what we can conclude here is, due to synergistic effect, due to back donation, the bond order of metal and carbon bond will increase, but bond order of carbon and oxygen will decrease. There is an inverse proportional relationship here. Here direct proportional relationship. More is the synergistic effect, means more is the synergistic effect means more is the effectiveness of back bonding. मेटल जितना इजीली इलेक्ट्रॉन पेयर को बैक डोनेट करता है CO मॉलिक्यूल में, उतना अच्छा सिनर्जिस्टिक इफेक्ट होता है. मोर इज द सिनर्जिस्टिक इफेक्ट, मोर इज द बॉन्ड ऑर्डर ऑफ मेटल कार्बन बॉन्ड, and less will be the bond order of carbon oxygen bond. And not only due to the synergistic effect, bond order will be affected, another bond parameter, bond length also will get affected. So what about the bond length? You know, generally bond order is inversely proportional to bond length. When bond order increases, bond length decreases. So here bond order of MC is increasing means bond length. So I need some space here. So due to synergistic effect, because bond order is inversely proportional to bond length, so bond length of CO, bond order of CO is decreasing due to synergistic effect, but bond length of CO it will increase, and bond length of MC it will decrease. Inverse proportional relationship. So this is a very important point that you have to note regarding the synergistic effect. So in any metal carbonyls you can find this synergistic effect. Now for example, if you take a metal carbonyl, for example Mn2CO taken 10 times. This is a coordination compound. Now, is this compound stable? Two manganese atoms are bonding only to 10 COs. Why? It is because of EAN rule. Both manganese present in this complex get stability according to EAN rule. That's why two manganese are bonded only to 10 CO, not less than 10, not more than 10. How can we explain this? Now, if you look at the structure of this complex, Mn, CO, 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 CO. Now, manganese is surrounded by, in this complex, 5 COs, 1, 2, 3, 4, 5. So, each CO will contribute 2 electrons. Total 5 COs around this manganese will contribute 10 electrons for bond formation. Now here there is a link between manganese and manganese. Metal-metal bond is present. This manganese is contributing 1 electron. This manganese is contributing 1 electron for bond formation. Now you have to take into account only 1 electron for this manganese out of this total complex molecule. Means equal division of electrons should be done. So contribution for bond formation from manganese side is only 1 electron, not the 2 electrons, because only 1 electron it can have in its valence shell. So it will contribute for bond formation. So totally, because manganese atomic number is 25, and from manganese side it is utilizing 1 electron for bond formation. So if you add, it becomes 26. Now to this 26, if you add a 10 electron contribution from 5 CO molecule, it becomes 36. It means this manganese atom has attained the krypton electronic configuration. Likewise, because it's a symmetrical molecule, this manganese atom same, it is having 26, and contribution from manganese is 26, and this COs 10, this comes to 36. So both the manganese atoms are attaining the noble gas configuration, that is krypton. That's why manganese will bond only to, each manganese will bond only to 5 COs. And manganese link is there. So this is the correct arrangement of Mn2CO 10 times molecule. So thank you for listening this concept.